Okay, so I think we should start. So welcome everybody to the second day of our mini workshop for the QFT and Geometry seminar series. So today we're going to have 6 more talks. So in the first block, we will have Morteza Hosseini, Sela, and Matteo Sacchi. And in the second block, we will have Antoine Bourget, Gianluca Zoccarato, and Luigi Tizzano. So the talks will be 5 minutes, 25 minutes plus 5 minutes questions. So I would ask the speakers to try to stay the 25 minutes and the audience to, if they can, wait to ask questions for the question time. Today we are going to have a longer break in between the 2 blocks of talks. So we will, after the third talk by Matteo, we will stop and we'll meet again at 3 p.m. Eastern. So I think we can start with the first speaker for today, Morteza Hosseini from IPMU. Please.
Thank you, Sarah, and thank you for inviting me to this nice mini workshop. Today's talk I'm going about, actually tonight's talk, so it's about anomalies, black strings, and the charge Cardy formula. So these are the ABC that I will discuss each one in more details in the next few slides. The talk is unfortunately a bit technical. I will try to put all the technicalities under the carpet and try to just say what the concept is. However, ugly formula will show up like in each slide or 2. So let me start with the introduction. As we know, all after the imaging of the Event Horizon Telescope, black holes are now firmly rooted in reality. And according to the Becken-Einstein-Hawking entropy law, the entropy of a black hole is proportional to the area of its horizon, or more precisely, in the Planck unit is equal to the event horizon, the area of the event horizon divided by 4g Newton constant. But the question that is the key question that has to be addressed by a consistent quantum theory of gravity is that where are the macrostates accounting for this black hole entropy? So this entropy, if it's going to be a thermodynamic entropy, it should have a macroscopic origin a la Maxwell-Boltzmann law. But this system, since these are like since we have a strong gravity effect, we need a consistent theory of quantum gravity, and a string theory provides as a prime candidate of a theory of quantum gravity a precise statistical mechanical interpretation due to the work of influential work of Strominger and Baffa, where they represented the black hole as the bounded states of extended objects in a string theory, which are d-branes. But curiously enough, this question has remained an enigma for more than 10 or 15 years, and people wondered how to proceed for asymptotically ADS spacetimes, where you have negative cosmological constant. This question looks easier because at least we have the ADS CFT correspondence, where the states in the holographic dual CFT should account for the black hole entropy, but there hasn't been any result until very recently by the work of Benini, Haristopoulos, Zaffaroni in the late 2015, where they employed holography and the technique of supersymmetric localization on the holographic field theory to reproduce the entropy of a first class of ADS black holes in 4 dimensions. These are solutions in n equals 2 gauge supergravity, and these are 1/4 BPS. Today's talk, I'm going to discuss the same line of thoughts where you reproduce the black hole entropy. This time I will focus on higher dimensions like ADS5 black strings. I will discuss what the black string is, and also ADS7 black strings, for which we count the states using n equals 4 Super-Yang-Mills or 62,0 theory. I'm not going to discuss ADS3 because ADS3 is very special. Almost everything is known about it. I mean, whenever you have an ADS3, definitely you have a CFT2, and you can employ the Cardy formula there and you're happy. So let me just forget about the ADS3 from now on. So let me start with the field theory part of the topic, which is the twisted compactification of 4-dimensional n equals 1 gauge theories. So let me start with considering this class of field theories that are placed on a torus times an S2. So here, the product is not a direct product, and the torus is actually warped over the S2. The way that we preserve supersymmetry over this S2 is by doing a topological twist, which is the simplest and yet, I would say, very beautiful way of preserving supersymmetry. You just need to turn on a U1R symmetry because you have n equal to 1, so you have a non-anomalous U1R symmetry. You can turn on a background gauge field in a way that you cancel the exact spin connection of the Kerr manifold. Here is the S2. So once you cancel this term with the background gauge field for the R symmetry, instead of having a covariant derivative on the killing spinor, you will have a normal partial derivative. So by choosing epsilon to be a constant, you can just get rid of the variation of the gravitino, and then you preserve supersymmetry. But the price that you pay by turning on this gauge field is to have a magnetic flux for the R symmetry. And one can actually do a more complicated twist by turning on some background fluxes for the various global symmetries that you have in the theory, and you have a more convoluted form of fluxes that I'm not going to discuss in the main talk, but I will mention some of the implications for future works. So from the holographic point of view, we start from a 4-dimensional CFT that lives on this 4 manifold. And then we will try to compactify with a partial topological twist the 4D theory on this S2, which has omega deformation. So this S2 is actually rotating. Once you compactify, this is not guaranteed that in the low dimension, you get a conformal field theory in 2 dimensions that lives on the torus. But thanks to holography, we constructed such solutions that have near horizon BTZ times S2. Again, this BTZ is warped over the S2 and S2 is rotating. And in the asymptotic, you have ADS5. So you have a holographic normalization group flow. And the existence of this BTZ geometry here is guaranteeing the existence of the 0,2 supersymmetric 0,2 CFT in the low dimensional field theory that is living on the torus. So the main question that I'm going to answer is how to reproduce this entropy of the corresponding black string in ADS5. These are called a string because they have the near horizon BTZ times S2 by counting the states in a holographic dual field theory. Okay, so there's no question, I think, during the talk, but I'm happy also to answer questions if there is something vague that I'm not explaining very well. Okay. Let me move on. So let me define the topologically twisted index of the 4-dimensional n equals 1 gauge theories, that is computing the partition function of these field theories placed on T2 times S2, where I denote the modulus of this torus by the tau and the omega deformation parameter by epsilon. It is defined, the grand canonical partition function, it is defined as the trace over the Hilbert space of states over S1 times S2 with the omega deformation parameter epsilon with an insertion of the usual -1 to the F, where F is the fermionic number. So you count bosonic and fermionic state with the sign. Q to the HL, where HL is the left moving Hamiltonian. You have the angular momentum contribution. So you turn on the fugacity zeta, which is e to the I epsilon over 2, is the fugacity for the angular momentum along S2, and you can have a bunch of chemical potential for the symmetry charges Q of the various global symmetry that exist in the quantum field theory. This object is very nice, very compact, but unfortunately, if I give you a full theory, you're not going to compute things using this formulation. So you need some more explicit formula. Happily enough, this was done by Benigni and Zaffaroni in a very nice work, and they use the supersymmetric localization to reduce the infinite dimensional horrible path integral to an other horrible but more nice matrix model. And this is given in the usual form of a matrix model. So as you can see, there is a counter integral over some meromorphic differential form. It is meromorphic and well defined on the torus under the condition that the gauge and gauge flavor anomaly of the field theories cancel, and those that we consider obey this condition. And on top of that, you have an extra sum over the various gauge magnetic fluxes that are living in the core root lattice of the gauge group, which I denoted by gamma H, and you have the usual factor of the symmetry, which is the order of the Weyl group of G. I'm not going to discuss the details of this, but I'm telling you that this has an explicit expression is given here. So you can see the classical contribution. The classical piece of the action does not contribute to this matrix model because it's Q exact. So there is no Yang-Mills contribution. And the one loop determinant for a chiral and the vector multiplet is given respectively by these two contributions. It depends on a bunch of dedicant eta function and the first Jacobi theta function. So I'm not going to tell you how to compute this matrix model, but always there's a way out in this game. So this is this one is very hard also to be solved at a large n, but there's a very peculiar limit, which is called Cardy limit, that simplifies your life. So let me define beta as the fictitious inverse temperature. It is called fictitious because we are dealing with supersymmetry. So there is no temperature, but this is like a temperature for us. And I defined it to be minus 2 pi I tau, and I take the limit that beta goes to 0. In this limit, you can use the asymptotic formula for the various Jacobi theta function and the dedicant eta function that you have in the matrix model and find the position of the poles and sum over all the gauge magnetic fluxes to obtain the following compact result. So let me spend some minutes on this formula to explain the details. So as you can see, let me just first focus on the first part of this formula. So this one, as you can see, is the usual Cardy formula that you would obtain by just looking in a two-dimensional CFT. You don't need any supersymmetry or anything. You just, if I ask you what is the asymptotic density of a space for a conformal field theory in 2 dimensions, you would just tell me it's the central charge of the theory divided by the beta. That's it. And this is actually the behavior that we obtain for 4-dimensional field theories that are placed on T2 times S2 with a topological twist along S2. So it's kind of like expected behavior that if you try to compactify on S2, you would obtain an elliptic genus on the T2. And this is the leading order behavior to that partition function. The central charge depends on the bunch of magnetic fluxes that you turn on due to the topological twist along the various global symmetries for the S2. And this is a trial central charge, which depends on the chemical potential delta that you turn on for various global symmetries inside the theory. And then there is a contribution from the omega deformation parameter. And you can see the second term is not really familiar to the 2-dimensional CFT per se. And it depends on a combination 3C minus 2A. These are the 4-dimensional C and A central charge of the field theory of the n equal to 1 SCFT. And these are trial with the mixing parameter P. For example, for n equals 4 super Yang-Mills, where you have SU4R symmetry, the carton is U1 cubed. So you can turn on 3 magnetic fluxes, call it P1, P2, and P3. And at large n, or for n equals 4 super Yang-Mills at finite n, C equals to A, and you get the contribution P1, P2, P3. It's just a multiplication of the 3 fluxes for n equals 4 super Yang-Mills. So this depends in a cubic way on the magnetic fluxes. So once you obtain this grand canonical partition function, what you do is to try to make contact with the black hole. But the black hole or the black string in gravity, the entropy of this class of black holes, it's written in the macrocanonical ensemble, not the grand canonical ensemble, and it depends on the charges, not the chemical potential. So what you would do is to perform a Legendre transform of this grand canonical partition function. And once you take the Legendre transform of this partition function, you trade the chemical potential delta and beta for the corresponding electric charges. Here, Q naught is actually the electric charge, which is the angular momentum inside the torus. So you add the momentum inside the torus, and then you can have an electric charge for that one. And then you have the omega deformation parameter epsilon, which is the true angular momentum along the S2. So let's not confuse these two. And once you have this, you extremize the right-hand side, you plug back the critical points into the object, and that has to reproduce the black hole or the black string entropy. I'm not going to construct the black string here. You need another 1-hour talk in order to introduce the supergravity context. But let me just tell you that for the ADS5 times S5 black string that we constructed explicitly, the following formula for the logarithm of the number of microstates definitely matches the one that we found from the gravity perspective with the coefficient and all included. Here, CCFT is the exact central charge of the CFT. So remember, this is the trial central charge, depends on the mixing parameter delta, the chemical potential. You extremize this object. Once you extremize it, delta is getting fixed in terms of the magnetic charges, and that is the one that gives you the CCFT. And the rest here are the electric charges, angular momentum, and A is the 't Hooft anomaly matrix, which I'm going to tell you how to compute it for various quantum field theory at hand. So having said this, these are all a ultraviolet perspective. So I'm telling you, for example, you have 4-dimensional n equals 4 super Young Mills or 4-dimensional n equals 1 CFT that you know the Lagrangian and all things about it. Then you compute the twisted index and you end up with this nice result. But the question that I'm going to answer in the next few slides is that what is the IR perspective? Can we derive such a behavior just by looking from the at the IR physics by computing the elliptic genus of this unknown 0,2 2-dimensional CFT, which is obtained by twisted compactification of the 4D CFT, or either you start from 62,0 and try to compactify in a 4 manifold, which is arbitrary manifold, and then you end up with a 2D CFT. Can you really count a state there without looking at the partition function, without going through the pain in order to compute everything? Let me say some words on that. So let me define the elliptic genus as the trace over the Hilbert space of S1 with the usual insertion of the -1 to the fermionic number. So again, I'm counting the state with the plus and minus sign for the bosonic and fermionic states. You have e to the 2 pi I tau. Tau is the modulus of the torus. HL is the usual left moving Hamiltonian. And you have a bunch of chemical potential and the symmetry charges J. So here mu A are holomorphic variables, while JA includes all non-R currents, which are left and right moving. Okay, so J has both left and right moving currents, but mu A are holomorphic variables. I'm not going to describe the subtleties that one will encounter in deriving the following charged version of the Cardy formula, but let me just say that if you apply the modular properties of this partition function, you can easily extract the leading behavior of the asymptotic density of the states for a generic CFT. Here I assume some supersymmetry, but this formula was obtained originally by Cardy in the context of ordinary non-supersymmetric CFT. So that's another interesting fact, that my formalism in the previous slides were just applicable in the case of SUSY, where you can do supersymmetric localization. But from IR perspective, you can really relax that condition and say that more few words about the non-extremal black strings in the gravity. Here, this formula is very similar to the one that I showed you in the previous page, and it's not actually very similar. It is exactly the same, as I will show in the next few slides. Here, CL is the left moving central charge, Q is the momentum along the circle inside the torus, and then K inverse AB is the inverse of the level matrix, which is just related to the 't Hooft anomaly matrix by an overall minus sign, and KAB is has to be positive definite because we are physicists for holomorphic currents. Okay, so having said this, as you can see, this logarithm of the number of microstates, the charge Cardy formula, only depends on the bunch of anomalies that you have. So if I give you a way to compute the CL and the K, the level matrix for various conformal field theory in the IR, you would definitely obtain the nice statistical interpretation for the black hole entropy in a holographic dual picture. So we already heard this in Pietro's talk. He gave a very nice introduction on anomaly polynomial, but let me just, to make the talk a bit more self-contained, say a bit more words. So anomaly polynomial characterizes the change of the phase of the partition function once you do some gauge transformation of the background metric or the gauge fields. And here, I will consider the manifold the total manifold to be T2 times, which is a Ward product, MD. In the previous slide, I just restricted to the case where MD was a two-dimensional sphere with the omega deformation. Here we can relax this condition and even have a more general manifold like the even-dimensional sphere or a Tori-Kaler-Einstein manifold. So I'm not here really putting any restriction at the moment. I'm using a notation where the ADD is the anomaly polynomial of a d-dimensional theory. For example, if I write A to D, this is the anomaly polynomial of a two-dimensional CFD, which is the four-form anomaly polynomial. Okay, this is just to set the notation. And we have a bunch of U1 symmetries in 2 dimensions, some of them originating from the parent conformal field theory, where you start with the number of U1s, global symmetry, and the others come from the isometry of the manifold itself. For example, in the previous case that I showed you, you have a bunch of global symmetries for the n equals 1 SCFD in 4 dimensions, and you have one extra one that comes because of the rotation along the S2. So in the first case, where you have the manifold M as an even dimensional sphere, you can apply the known Bott-Cattaneo formula. Actually, this Ibo and collaborator has a couple of nice papers on the topic, and they really showed the beauty of this formula, how to get the bottom of this application of this Bott-Cattaneo and how to understand things better on this side. Here I'm going to discuss this in a context of, in a context that is more related to holography, not pure field theory. And also I will generalize the computation and for the manifold MD, which is not an S to the power of 2k, but rather a manifold with isometry group U1 to the n. Here, I will use the equivalent integration of the anomaly polynomial, and I will give you some examples how to proceed when things get convoluted. But let me recall that in order to obtain the anomaly polynomial of a lower dimensional field theory, we just need to integrate the one in the higher dimensions over the compact manifold MD. So you obtain the lower dimensional field theory. Okay. So let me start with the simplest case scenario where you have an S to the 2k as the compact manifold. So let V be a real 2k plus 1 dimensional vector bundle over the base manifold B and take the unit sphere at each fiber so that we can have a S2k bundle E over B. The Bott-Cattaneo formula is simply stating that the integral of the Euler class to the odd power equals to the 2 times the case Pontryagin number of the vector bundle V to the power of S. So this is for the odd power, and all the even powers of the Euler class integrated over S to the 2k is just vanishing. For example, the simplest case scenario, let's set S equal to 0. So you just integrate the Euler class over the S to the 2k, and you get the 2, which is the Euler number of S to the 2k. So as you can see, if I go, for example, to the anomaly polynomial and try to compute things, and if I encounter e to the power of 3, this is not going to be 0 anymore because this is proportional to the case Pontryagin number to the power of 1 here. So let me move with the manifold with isometry U1 to the power of n, and let me emphasize that the computation involves only a combination of Pontryagin classes of the spacetime manifold over which you put the conformal field theory, and characteristic polynomials of the background gauge field of the original conformal field theory that you start with, and the background gauge field for the isometry of this manifold M. And let me also say that these classes are independent actually of the base B and the line bundle E, and you can have a rigorous way of defining these universal classes. By rigorous, I mean like mathematically rigorous, and this is what makes up the G equivariant cohomology group. So the cohomology classes involved in this computation are all universal, and you can use the G-equivalent cohomology group in order to define those classes. And here I denoted by the G-equivalent cohomology group by the U1N bullet MD, where on the right-hand side, you have the first factor, which is the ordinary cohomology group. And the second one is just the first-term class along the base B of the background gauge field of the IC1 isometry. And I take the coefficients to be real. The most convenient way to do the integration over the anomaly polynomial is here to use the localization formula. I will assume from now on that the manifold that I'm dealing with has a discrete isolated fixed point. So for example, you can have toric-Kähler manifolds. And for this class of manifolds, you can actually integrate an element of the cohomology of the M by just summing over the number of fixed points. In the numerator, you have the cohomology element omega, which is restricted to the fixed point P. And in the denominator, you need to compute the Euler class, which is a bit more convoluted to be defined. Let me try to explain it a bit. So this is in order to compute the Euler class of the tangent of the manifold M, which is restricted at the fixed point P, we can consider the tangent space to be a complex vector bundle. And this complex vector bundle, I can consider it as the sum of the complex line bundles, which I denoted by LJ. So the tangent space itself is a complex vector bundle, and I consider it as a sum of the complex line bundles. And I consider LJ to transform under a definite charge under the U1 to the power of n, which is the isometry of this manifold. And then it's easy to show that this Euler class can be computed in the following way. So you just have a product over J. J goes from 1 to the n,
sorry,
the number
Morteza,
of the U1s.
Morteza, sorry, you just passed 25 minutes, so maybe you can just try.
Okay, I will wrap up then.
Yeah,
it's okay. So you compute the Euler class, and I mean, having back this here, you can compute the localization formula. But let me just give you an example just to see how this works. You can consider the M to be the S to the 2K, where you have the isometry U1 to the K. There are two fixed points at the north and the south pole of the sphere. You assign plus and minus charge to these two poles, and then you can write down the following formula, which is the sum of the two fixed points. And then you obtain this following formula, which is just the first term class of the symmetry J to the power of 2s, and using the relation between the K-point tracking number, you obtain the exact Podkatanow formula. Okay, I'm going too fast, but believe me that this is just too simple. So I'm not having time in order to explain more detail on n equals for super Young Mills, but the same computation can be done for n equals for super Young Mills and also for 62,0. I'm not having time to explain all the thing, but let me just tell you that the final result is going to be the charge Cardy formula for 62,0 or n equals for super Young Mills, which indeed reproduces the black hole entropy. I think I will finish my talk here with the outlook for the people to look.
Okay, thank you. I think now we have time for one question or so. If you want to ask a question, just unmute yourself and go ahead.
What do you mean with non-abelian twists?
Oh, so you can consider like from gravity perspective, you need to have a negatively curved background, like a hyperbolic manifold. So if you have a hyperbolic manifold, then you can do a non-abelian twist like Donaldson-Witten or some other twist. And then you can ask the question if the gravity object exists and how the anomaly polynomial looks like, and if the charge Cardy formula changes and how it gets modified.
Okay, thanks.
Any other urgent question? Okay, maybe we'll have another round of questions at the end of the three talks, and so we can take another chance to ask your question. So we thank Morteza for the nice talk. And so next up is Or. So please, you can share your slides.
Yeah. Okay, so you can see that, right?
Yes.
Okay.
Maybe you can go full screen.
Yeah.
Okay, good.
Okay, so I would like to thank you, the organizers, for giving me the opportunity to speak here. And I will talk about the nilpotency index of conformal manifolds. So I'm Or, and this is based on a recent work with Zorko Magotsky, Shlomo Razamat, and Adar Sharon. Okay, so the plan is to first start with some background motivation, and then I'll show the main argument, and then I'll finish with some examples and future directions. Okay, so the main object that I'll consider is the conformal manifold, and these objects exist mostly in supersymmetric theories, and indeed without supersymmetry. So for example, in 2 dimensions, they're not expected except in the case of where the center charge is equal to 1. And in higher dimensions, there are not known examples yet with finite central charge. So what we'll do is to focus on supersymmetric theories with 4 supercharges. So you can bear in mind 4dn equals to 1 theories or 3dn equals to 2 theories. So each point P of a conformal manifold is a superconformal field theory. And to move along the conformal manifold away from a given point, we should deform the action by such an exactly marginal deformation, where in this green formula, O are exactly marginal operators and Q is the supercharge. So I'll refer to O as the exactly marginal operators, even though the deformation itself is descendant. And then we get, using these exactly marginal operators and deformations, we get a space of superconformal field theories with local coordinates h being here the parameters that we use in the superpotential. Okay, so now the exactly marginal operators O are chiral primaries of dimension d minus 1. So in particular, at any point P of the conformal manifold, there are non-trivial elements of the chiral ring. And we would like to examine the relation between these 2 roles that are played by the exactly marginal operators. So on one side here we have the conformal manifold, and the exactly marginal operators are used to move along it. So we're using them in order to deform the theory and flow to another superconformal point P plus delta P, let's say. On the other end, at each such point P, we have a theory and we have a chiral ring and a space of vacua. And these 2 are closely related in the sense that if we discard nilpotent elements from the chiral ring, what is left is isomorphic to the space of holomorphic functions on the supersymmetric vacua. So at each such point, we have a chiral ring and a space of supersymmetric vacua, and the exactly marginal operators O can also be used to parameterize this space. So we can both use them to move along the conformal manifold, and also at each point use them in order to parameterize the moduli space of vacua, or serving as a non-trivial element of the chiral ring. So they're used in parameterization in both spaces. Now, the main argument that I would like to discuss is that at generic points of the conformal manifolds, and a generic, I mean, apart from complex codimension 1 or higher codimension subspaces, the operators O, by which I mean the exactly marginal operators, have a vanishing vacuum expectation value. So this is what I would like to show. And this results in the fact that at such generic points, the exactly marginal operators are nilpotent elements of the chiral ring because they have a vanishing vev. So they exactly belong to this part of the chiral ring that we should dismiss in order to get the part that labels the vacua. So they're non-trivial elements of the chiral ring, but they should be nilpotent because the vev is 0. And then this implies that since we consider chiral ring operators and relations that depend only on the presence of conformal manifold, so consider chiral ring relations that as a function of complex parameters that are themselves background chiral fields, everything is holomorphic, and such nilpotency index K can only jump along complex codimension subspaces. And then this means that we can, that these spaces are of even real codimensions, so we can always bypass them and define a global integer invariant of the conformal manifold, which is the nilpotency index at generic points and directions. So to claim this, we would like to examine the possibility that the wave is not zero. So let's consider a superconformal field theory at a point P in which the R and conformal symmetry is spontaneously broken. So if we do give O a wave, then of course it breaks. So it has dimension 3 and R charge 2, so it breaks both R and conformal symmetries. So let's look at the point P in which we have this R symmetry breaking vacua, and focus on this for the moment. Not necessarily ones that have non-vanishing wave for O, but ones that have the R symmetry broken. And in this vacua, the effective superpotential takes this IR form. So here psi is the R axion superfield that results from the R symmetry breaking vacuum, from the breaking of the R symmetry. And X are just R neutral chiral superfields. So we have this general form that we know the superpotential takes due to R symmetry breaking. So now we would like to see how this effective theory looks at generic points on the conformal manifold. So let's consider some generic deformation from the point P to a point P plus delta P. This is done, as we said before, using such a deformation. In terms of the low energy fields, such O has general characteristics that are like the superpotential itself. So it has, for example, R charge 2. So it will take a similar form with G some function. So now the effective theory would look like this. So this is what we had before, and this is the new piece, a generic points H. And now let's consider a supersymmetric solution, a supersymmetric vacuum solution. And it satisfies these two vacuum equations. So they result from this superpotential. So we have this simple vacuum equations. And now, since this equation is satisfied, so we assume some generic H, so it is satisfied on some generic values of H, and we can in particular differentiate with respect to H. Since this is 0, so the derivative would be 0. And then we get two contributions for the derivative. The first one from the fields X, that because they depend on H themselves. So we differentiate with respect to the fields X, so the partial derivative with respect to X, and then differentiate X with respect to H, plus the part that depends explicitly on H, which is just G. And then we're left only with G because this part includes the derivative of this piece, which is exactly this second equation. So applying this second equation, we're left only with G, and recall that G is how we represent O in this low energy theory. So this means in particular that the wave of O is 0. So we showed that if we consider here supersymmetric solutions that depend nicely on some parameters H of the conformal manifold, then we get that it's not supersymmetric, it's not R symmetry breaking vacua, the wave is 0. Let me also comment that at special places on the conformal manifold, new vacua can appear. Then this argument does not apply because X is not will not be an analytic function of H. Actually, it will not be continuous, and then O can get a wave. But this is, of course, only happen at some special points. It's not a generic behavior. Here, I assume the generic behavior. So we showed that at generic points of the conformal manifold, the exactly marginal operators have a vanishing vacuum expectation value. Therefore, the nilpotent elements of the chiral ring. here is a simple illustration of the argument. So here we have a two-dimensional conformal manifold parameterized by O1 and O2. These are two exactly marginal operators. At each point, we have a superconformal field theory with some moduli space of aqua. And here we have an example in which this line that I'm pointing, the O1 line corresponding to, say, H2 equals to 0, is a special locus in which O2 can get a VEV. So we see that we can have some here a complex codimension 1 subspace in which some of the operators can get a VEV. But once we deform away from this locus, we get that the VEV of O2 is 0, and specific and more generally at generic points P plus delta P3, all the expectation values of all the exactly marginal operators vanish. So here it just demonstrates that this cone is tangent to the conformal manifold, just to say that O2 has a non-vanishing VEV here, but otherwise has a vanishing VEV. Okay, so we claimed so far that at generic points we expect the exactly marginal operators to be nilpotent. Now let's turn to see some examples in which this nilpotency can be easily demonstrated and in some cases even calculated. So let's start with a simple example of a U1 vector multiplet in 4 dimensions. This is an n equals to 1 multiplet. So this is just a free theory containing a photon and a Weyl fermion. And in particular, the operator W squared, where W is the field strength chiral multiplet, is exactly marginal. And the corresponding parameter is just the gauge coupling. So this is a 1-dimensional conformal manifold parameterized by the gauge coupling, which seems trivial in here in flat space, but in curved space it is not trivial. And then due to Fermi statistics, we simply get that O squared is 0. So here it is indeed a nilpotent operator with nilpotency index being equal to 2. Now let's turn to n equals to 2 theories in 4 dimensions. And let's look at them. So we consider n equals to 2 conformal manifolds, but we view them as n equals to 1 manifold. So we use n equals to 1 notation. In particular, the manifest supercharge in this description would be Q1 and Q2 would be the other set of supercharges. So the exactly marginal operators that are used to move on this manifold are denoted as usual by OI, and there are n equals to 1 chiral primary operators of dimension 3. This is regarding the n equals to 1 notation, but since we're in n equals to 2 theory, in the n equals to 2 superconformal algebra, they're actually descendants of Coulomb branch operators of dimension 2. So they are obtained by Q2 squared applied on some Coulomb branch operator, which is n equals to 2 chiral operator. And then it means that since every n equals to 1 preserving vacuum is also n equals to 2 invariant, it means that the VEV is 0. So we see that all the exactly marginal operators in an n equals to 2 theory are nilpotent everywhere on the conformal manifold. So here we don't have these special places where they can get a VEV. Here they are nilpotent everywhere. Let's now turn to 3 dimensions and look at this simple Wess-Zumino model. So we look at a 3D n equals to 2 Wess-Zumino model. We have here 3 chiral fields X and this cubic superpotential. And this superpotential is relevant in the UV and it flows in the IR to a fixed point. It is part of a 1-dimensional conformal manifold. It is parameterized by the ratio of lambda 2 and lambda 1. So we called it H as usual. This is the parameter on the conformal manifold. And here a generic point H on the conformal manifold, the chiral ring is finite and consists of these elements. So at our charge 2/3, we have the 3 chiral multiplets, x1 up to x3. At our charge 4/3, we have 3 chiral multiplets which take these quadratic forms. These are equivalences that result from the chiral ring relations. So for example, x1, x2 is equivalent in the chiral ring to x3 cubed. So we have only 3 inequivalent elements in the chiral ring. And at our charge 2, we have only a single element in the chiral ring, which is given by all these different forms. And this is the exactly marginal operator. And we don't have any other operators at higher R charge. So in particular, this means that O squared is 0 in the current ring, and that the nilpotency index is 2. So we see that it is nilpotent and the nilpotency index is 2. Now let's turn to a less trivial example. And let's consider n equals to 4 super Mills theory in 4 dimensions with gauge group SU2. So in n equals to 1 notation, I'm denoting the representations like this. So as a pair, the first one is the representation under SU2, the SU2 gauge group. The second one is under the SU3 global symmetry. W is the field strength chiral multiplet as before, which is in the adjoint representation of the gauge group SU2 and in the singlet of the global symmetry. And phi is the chiral multiplet, which is in the, again, in the adjoint of SU2, but now in the triplet of the SU2, SU3 global symmetry. And we have the well-known superpotential, which is just a phi cubed, of course, taking the singlet of both representations. And we have a conformal manifold, which is parameterized by H. And due to n equals to 4 supersymmetry, H is related to the gauge coupling. So as I said, we have a one-dimensional conformal manifold, and the exactly marginal operator is not phi cubed, but it is a combination of phi cubed and the global operator, which is this W squared operator. But of course, we can in the chiral ring regard it as phi cubed because we have the Cornish anomaly that relates these two. So for example, if we consider the anomaly equation of, let's say, a U1 that rotates a phi with a charge third, such that phi cubed has a charge 1, we have this anomaly equation for this. And since the left-hand side is cube-or exact, it is 0 in the chiral ring. And we get that the left-hand side is also 0 in the chiral ring, and therefore that S is equivalent to phi cubed in chiral ring, and we can take the exactly marginal operator just to be S. Now, as this is a theory with higher supersymmetry, and as we showed before, n equals to 2 in 4 dimensions already shows that all the exactly marginal operators are nilpotent. So we know that O is nilpotent, and it will be interesting to try to find its nilpotency index. So to do this, we first notice that classically, we can show that S squared is 0. And this was showed for general SUM gauge group in a paper by Kachazo, Douglas, Saberg, and Witten. And so this is a classical relation. And what we would like to do is to find whether it receives quantum corrections in the full quantum theory. And to do this, we investigate this more general relation. So the possible quantum corrections can only take this form. So where H is F is a holomorphic function that vanishes at the free point, and P is some nilpotent scalar chiral primary operator that should have R charge 4, and of course it should be a singlet of the global symmetry if it's to be related to S squared. And it should not be given by S squared, phi cubed squared, or S phi cubed, because otherwise it will result in the same relation. So this classical relation would not be modified. We are looking for an operator P that can modify the classical relation in such a way that would result in a different chiral ring relation in the quantum theory. So of course we should not look for these operators which are all the same in the chiral ring, because recall that we have this relation. And so, the question is whether we have such an operator P in the theory. And if we look at the quantum chiral ring, at R charge 4, then it consists of this bunch of operators with these representations. And the only operators here which are singlets under the global symmetry are exactly these 3 operators, which are exactly these 3 operators listed below. So they are just S squared and phi cubed squared and S phi cubed. So we see that we don't have an operator P in the theory that changes the S squared equals to 0 classical chiral ring relation, and therefore S squared is 0 also in the quantum theory, and we get that the nilpotency index in this case is 2 as well. Now let's turn to an n equals to 1 example in 4D. So let's consider SQCD with SU3 gauge group and 9 flavors. And this theory has a 7-dimensional conformal manifold. And we'll consider a 1-dimensional locus, which is parameterized by this superpotential. So on this line, we have 9 quarks, and there are, the SU9 global symmetry is broken to 3 copies of SU3. So if we have a 1 quark in the fundamental of SU9, we break it to 3 quarks in the fundamental of SU3, of 3 different SU3s, and the same for Q tildes, which are the anti-quarks. And then we have this superpotential, and this is an exactly marginal operator with parameter h, and we consider this 1-dimensional locus inside the 7-dimensional conformal manifold. And I did not do representations like this, so this is the representation under the SU3 gauge symmetry. And here we have 3 SU3I symmetries, and here 3 SU3I tildes symmetries acting on the Q tildes. And by a vector of singlets, I mean just a bunch of 3 singlets. So this is the theory we consider, and the 0 point h equals to 0 is just a free theory. And the global symmetry is U9 times U9. But at non-zero coupling, both of the U9s, both of the U1s are broken. So the U1 of this U9 and the U1 of this U9 are broken. And as we said before, each SU9 breaks to 3 copies of SU3. So let's consider in more detail this breaking of global symmetry and see how it affects the chiral ring relations. So the broken off diagonal currents of this SU9 breaking to 3 copies of SU3 are these currents, and they recombine with this kind of baryons. So we have 2 copies of one quark, another with another quark. So there are baryons that are labeled by two indices, and I is different from J, and we have this non-conservation equation. Again, not at the free point, but at H, at some generic H. And in addition, we have 2 U1 symmetries that are in the Cartan of SU9 and that are not in the Cartan of either of the SU3 symmetries. And we have for them these non-conservation equations as well. And as before, since the left-hand side is non-zero and the chiral is Q-bar exact, this is 0 in the chiral ring. So the right-hand sides of all these equations are also 0 in the chiral ring. And we get that all the baryons with 2 indices are 0 in the chiral ring. And all these baryons with a single index, which are just Qi cubed, are just equal to each other. And the same applies for the Q tildes. So overall, we get that all the baryons with 2 indices are 0 in the chiral ring, and all the baryons with 1 index are equivalent to each other. And applying the Konishi anomaly for some U1, for either of the U1s or belonging to U9, like in the previous example, we get that not just that all these baryons are equivalent to the chiral ring, they are also equivalent to the global superfield. So we can just take the exactly marginal operator to be the global superfield S, as in the previous example. And so the chiral ring is now generated by the global superfield S and the meson, and we still have 2 kind of baryons with no indices at all, that are these 2 baryons. So these are the generators of the chiral ring. And as in the previous example, S cubed is classically 0, and we would like to see whether there is an operator P such that S cubed plus this P times some holomorphic function that vanishes at the free point is 0. And then the classical relation S cubed equals to 0 is modified quantum mechanically. So again, we look for an operator P, which is nilpotent, is scalar and chiral primary. And it has R charge 6 and is the singlet of the global symmetry, of course. And it should not be equivalent to S cubed because we want to examine operators that will result in an inequivalent chiral ring relation. So doing this, we see that the only way to do this is to take this meson squared times S. This is the only way to form a singlet out of this bunch of operators, and this is the form. So we take cube, the third power of the mesonic operator. This is a singlet under the global symmetries, and time the global. This is a possible candidate for P, but there is another relation which looks like this. So taking the third power of the meson, gives us just the product of the two baryons with single index, which is just S squared. So multiplying by S, we again get S cubed, and so it does not result in an equivalent Carry ring relation. And so we see that we don't have certain operator P in the theory, and that as a result, the exactly marginal operator S is nilpotent, and its nilpotency index is bounded by 3. So I'll summarize what we saw. So we saw that exactly marginal operators are nilpotent elements of the Carry ring and generic points of the conformal manifold, and that this endows the conformal manifold with a global integer invariant K, which is the nilpotency index at generic points. And sometimes some interesting future directions would be to look at conformal manifolds that have some weak coupling corners. So sometimes, so there are examples for such conformal manifolds that are conjectured to have these weak coupling corners, and it would be interesting to compute the nilpotency index and test such conformal dualities. So it would be by computing this for the different weak coupling descriptions, and then see whether it matches. And since this is an invariant, it should match, and it would provide a non-trivial check of the duality. And it would be also very interesting to find a general way to find this nilpotency index. In particular, natural questions are whether this index can be extracted from a supersymmetric partition function of some kind, or is it not the case, and then it is a new invariant. So it will be very interesting to further pursue these questions. So thank you.
Thank you very much. So we have time for one question or two. Sakura has a question.
Yes.
Yeah, really nice talk. Thanks. Quick question. Is there a reason why you don't consider 2D theories with 4 supercharges like 2,2 or 0,4? Is it trivial in this case, this nilpotency index?
Yeah, exactly. So
it's trivial, okay.
Yeah. So in 2 dimensions, the Carry ring is finite, so all the operators are nilpotent. So yeah, it's another example. It's another trivial example for this argument. It adds a nice thing because most of the examples I showed as nilpotency index 2, because these are the easiest examples to fully analyze, but and to get the actual answer. But if you in 2D, it is more tractable, and you can actually calculate the nilpotency index. And then you can have many examples of theories in which the nilpotency index can take any number. So and then you can show it's not just 2 or bounded by something. So it's in one hand it is trivial, in the other hand it's interesting to calculate the index itself in such theories. Yeah.
Cool. Thanks.
Any other question?
So maybe I have a quick one. So in the case of n equal 2 and equal 4 theories, I had the impression that you consider deformations which are n equal 2 and n equal 4 preserving, right? You consider not a generic n equal 1.
Yeah. So generically, yes.
Specific. So why don't you try to consider? I mean, there is a reason why you do that, or did you try to consider the case of a generic n equal 1?
Yeah. So first of all, the general argument works for n equals to 1 theories. So for example, if we go back to let's go back to this. No. I'm trying to go back to the example of the n equals to 4 super Mills theory. So yeah, so here I considered an n equals to 4 theory with SU2 gauge group because it's easier to analyze. If the gauge group is SU3 or higher, then you also have a broader conformal manifold, which is a 3-dimensional, and consider, and this is an n equals to 1 manifold. And this n equals to 4 theory is just a specific line. So so of course you have cases in which the conformal manifold is n equals to 1, and it contains special loci in which the supersymmetry is enhanced. Our argument works generally for n equals to 1 manifolds. What I showed in the case of higher supersymmetry is that it is easy to show that the operators are nilpotent everywhere. but of course, it's not specific to these theories. So you can have, if we have a conformal manifold with n equals to 1 supersymmetry, then you have some nilpotency index, and then you can have a special locus with higher supersymmetry. And then on this special locus, you can apply the argument again, and you might have a different nilpotency index. Because in the n equals to 1 framework, this only happens in generic points, but since the higher supersymmetry happens at non-generic points, then the nilpotency index might be different, but still the operators that are used to move along this special locus are also nilpotent by applying the argument again. So, so the answer is that yes, I mean the operators are nilpotent on the n equals to 1 on the larger n equals to 1 manifold, and also on the special locus with higher supersymmetry, but they might not have the same nilpotency index because we define it at generic points.
Okay, yes, thanks. But you didn't check for SU3 gauge group, for example, that the index is different if you move along?
No, because then you have candidates for this operator P that might change the classical Cardy ring relation. So it's harder to argue this.
Okay.
Okay, thank you. So perhaps we, as I said, we will have some more question time at the end of the third talk for all the speakers. So maybe we can move on to the next. It's Matteo Sacchi. So,
okay, I'll stop sharing.
Yes, please.
Okay. Can you see full screen?
Yeah, I think you can go ahead.
Okay, thank you. And I would like to thank the organizers for the possibility of presenting my work in this nice workshop. So in my talk, I will try to give you an overview of some papers that I wrote in the last couple of years with Sara Pasquetti, Shlomo Razamat, Gabi Zafrir, and Chung Wang. And toward the end, I will also mention some work in progress. So let me start by trying to give you the general picture of our work. So the ultimate goal is to try to understand better the dynamics of supersymmetric gauge theories, especially in 4 and 3 dimensions. And for this purpose, by now we know many tools that we can use. And here I just wrote the two that will play an important role for my discussion. So one thing that we can do is to use correspondences. In particular, I will be interested in gauge CFT correspondences. And my perspective on this will be that we can try to use known results on the CFT side of the correspondence to find instead new results on the gauge theory side. Another tool that we can use is flows across dimensions that connect theories in different dimensions. And in particular, I will be interested in flows from 4 to 3 dimensions and from 3 to 2 dimensions that are engineered by circle compactifications. So the idea is that we can try to combine these various approaches to create a larger web of connections that then we can use to indeed understand better the dynamics of 4 and 3-dimensional supersymmetric gauge theories. And in particular, I will be interested in 2 aspects, which are infrared dualities and enhancements of global symmetries in the infrared. Another thing that I would like to mention is that in the last years, we saw another very powerful approach to the same type of questions, which is a sort of geometric program in which we can try to systematically construct 4 and 3-dimensional theories by compactification from 6 dimensions. And with this construction, we can usually understand the infrared dualities and symmetry enhancements in a geometric way. But instead, what I will tell you about in this talk is another strategy that in a sense goes in the opposite direction because it will be more of a bottom-up strategy. But before coming to this point, let me present what are the limits that I will be interested in. So the starting point is in 4 dimensions, where I will always consider theories with n equal 1 supersymmetry. And for example, we can take a pair of theories that are dual in the infrared. And one question that we can ask is if this duality is preserved when we flow to 3 dimensions. So by this, I mean that we can compactify both the 4-dimensional theories on a circle, so that when we flow to low energy, we get a pair of effective 3D n equal to 2 theories. And we can try to understand if these theories are also dual in 3 dimensions. This type of question was first investigated in 2 papers by Aroni, Razamat, Seiberg, and Willett. And by now we quite well understand how to perform this dimensional reduction from 4D dualities to 3D dualities. Now that we are in 3 dimensions, we can perform a further circle compactification to flow to 2D. And on this other limit, I will actually take a particular perspective. In particular, I will consider the 3D duality at the level of the S2 times S1 partition function, which is also known as the superconformal index in 3 dimensions. This observable can be computed with localization techniques, and it takes the form of a matrix integral. In particular, the dimension of the integral is equal to the rank of the gauge theory in 3 dimensions. And the duality basically translates into non-trivial integral identities for this type of complex matrix integrals. Now, what I'm interested in is studying this 2D limit at the level of this S2 times S1 partition function. And we observed that if we suitably take this limit, then this partition function reduces to a complex integral, which appears in an apparently unrelated topic, which is the one of CFT free field correlators. So by this, I mean CFT correlators that are expressed as a correlator in the free theory with the insertion of some screening charge operators. So under this sort of gauge CFT correspondence, the dictionary is that the rank of the gauge theory, of the 3-dimensional gauge theory, is equal to the dimension of the complex integral, which is also equal to the number of screening charge operators. Now, the idea is that if we take this limit on both sides of the 3D duality, we get an integral identity between 2 different complex integrals, which is essentially giving us an alternative form for this free field integral. So this is the logic of the limits. And this is an example in which we can really take all these limits explicitly. So in this example, the starting point is a 4D n equal 1 duality for a USP2 gauge theory with 1 antisymmetric chiral, 6 fundamental chirals, and some gauge singlets. And the dual theory is a Vezzo-Mino model. So there is no gauge interaction. We just have a superpotential interaction among the chiral fields of the theory. Now, from this duality, we can get a 3D n equal to 2 duality by performing a circle compactification. And moreover, in 3 dimensions, we can also perform a real mass deformation, which basically has the effect of breaking the symplectic gauge group down to a unitary gauge group. So in 3 dimensions, in this way, we get a duality between a UN gauge theory and again, a Vezzo-Mino model. Now, the next step is to consider the equality of the S2 times S1 partition functions associated to this duality. And what we observed in this paper from last year is that if we suitably take the limit in which the circle is shrunk to a point, then what we get is that the partition function of the gauge theory reduces to a complex integral, as I mentioned before, which coincides with the free field integral representation of the 3-point function of Liouville theory. So here I'm not showing you explicitly what is this complex integral, I'm just calling it C, but as I mentioned before, the dictionary is that n, the rank of the gauge theory, is equal to the number of screening charges that appear in this free field integral. And moreover, the 3 momenta of the 3 operators are related to some parameters for the global symmetry of the 3-dimensional theory. Now, what happens on the dual side? Here we have a Vezzo-Mino model, so there is no gauge group, which means that there is no integration in the partition function. And so if we take this limit on both sides of the duality, what we get is really an evaluation formula for this free field integral of the 3-point function of Liouville theory. So we recovered in this way what is known as the DOCC evaluation formula for the 3-point function of Liouville. So the question that now I would like to ask is the following. Can we somehow reverse the logic of these limits? So more precisely by this, I mean the following. Once we have really understood how all these limits work, we reach a point in which if we are given a 2D CFT free field correlator, a complex integral of a free field correlator, then we can immediately read out of it a 3 or a 4-dimensional gauge theory. And then using this knowledge, we can try to understand if some known results for 2D free-field correlators translate into non-trivial unknown properties that this gauge theory exhibit in the infrared. So what I will do in the following is show you some examples that we have in which we managed to successfully apply this bottom-up strategy. So for the first example, we can look at some results from a paper by Fatev and Litvinov. Fatev and Litvinov studied these free-field correlators in Liouville theory, and they basically managed to manipulate these free-field integrals and write them in terms of an auxiliary object, which they call the kernel function. This is basically a function which has a definition in terms of a very complicated, complex integral, but despite being complicated, is exactly of the same type that we get from the limit that I mentioned before of the S2 times S1 partition function. This kernel function that I'm calling K has a remarkable property. It depends on two sets of parameters, X and Y, and it is symmetric under the exchange of these two sets of parameters. So our strategy is to look at the complex integral definition of this kernel function and try to read out of it a 3D n equal to 2 gauge theory. So the gauge theory that we found is what we call the MSUN theory, and this is what it looks like. So in this quiver representation, I'm using a 3D n equal to 2 language. So all the lines represent chiral multiplets, and as usual in quiver notations, all the circle nodes are gauge groups, while square nodes are global symmetry groups. And in my notation, the blue colors denote unitary groups. Moreover, I'm also highlighting the fact that the fundamental monopoles of each gauge node are turned on in the superpotential. And this is the reason for the M that we gave in the name of the theory. Now we can try to understand if indeed the properties of the kernel function translate into some properties that this MSUN theory possess. The first one is an enhancement of the global symmetry in the infrared. In the UV, we have a manifest SUN symmetry and a bunch of U1 symmetries, but these U1s are enhanced in the infrared to a second SUN. So these two SUN that the theory has in the infrared correspond to the two sets of parameters of the kernel function. And the symmetry property of the kernel basically translates into a self-duality of the theory. So this means that the theory is dual to itself, but with a non-trivial map of the global symmetries. The two SUNs are exchanged. Now, an interesting observation is that if we look at the form of this quiver and at all of these properties that I just mentioned, they really remind us a lot of the TSUN theory of Gayatto-Witten. And indeed, we managed to show very explicitly that there exists a real mass deformation that makes us flow from MSUN to TSUN. And under this flow, the self-duality of MSUN reduces to the known self-duality under mirror symmetry of the TSUN theory. So this is an observation that will be important in a moment. But for now, we can remember that our starting point originally was in 4 dimensions. So the natural question now is if there exists a 4D n equal 1 ancestor of this theory. And indeed, it exists. It is a theory that we called EUSP2N theory in this paper with Sarah, Shlom, and Gabi. And the name is due to the fact that now all the groups are symplectic groups. So I'm using the black color to denote them. This theory represents probably the only point in which we can make contact between our bottom-up strategy and the more standard approach of compactification from 6 dimensions that I mentioned at the beginning. Indeed, the reason why we introduced this theory in our paper was because it plays a crucial role in the compactification of the 6-dimensional Rankine string theory or Riemann surfaces with fluxes. In particular, it is associated to the theory obtained from compactification on a tube, a sphere with 2 punctures. Another important observation for us was that the supersymmetric index of this theory as an integral function coincides with an object that was studied in details by a mathematician, Rines, And in particular, Rines managed to prove several non-trivial integral identities for this function that we can understand as properties that this USP2N theory possesses. And these properties that I will mention in a second are very, very reminiscent of the same properties that I showed you in the previous slides for the three-dimensional MSUN theory. So the first property is again an enhancement of the global symmetry in the infrared. In this case, in the UV, we have a USP2N factor and a bunch of SU2 symmetries. And these SU2s are enhanced in the infrared to a second USP2N. And then also this four-dimensional theory enjoys a self-duality, which again acts exchanging the two USP2N symmetries. All these similarities between the USP2N theory and the three-dimensional MSUN theory are not an accident, because indeed we can flow from one theory from the other. And this flow is engineered by first a circle compactification, and then again this real mass deformation that breaks all the symplectic groups down to unitary groups. Now, if we remember that then we can flow from MSUN to TSUN, we immediately understand that this USP2N theory and its self-duality can be really understood as a four-dimensional ancestor of the mirror self-duality of TSUN. By ancestor, I mean that by circle compactification, we can flow from one to the other. And we found this observation quite interesting because, as I mentioned in the introduction, by now we quite well understand how to perform the dimensional reduction of 4D dualities to 3 dimensions. But in this way, we are able to reproduce only 3-dimensional Seiberg-like dualities. But in 3 dimensions, we also have this other type of infrared duality, which is mirror symmetry. So this seemed to be the first example in which we managed to find such a 4D ancestor for mirror symmetry. And so we wondered if it was just an isolated example, or if we could find other examples of this new type of 4D n=1 infrared duality that by analogy we called mirror-like duality. So for this slide, I will change topic a little bit because these results are not a direct uplift of results for 2D CFT free field correlators. Instead, to find these 4D mirror-like dualities, we took inspiration from 3 dimensions. Indeed, in 3D, the TSUN theory actually belongs to a larger class of theories, which are linear quiver gauge theories with unitary gauge groups. These theories are generically called T sigma rho of SUN theories, because sigma and rho, which are 2 partitions of n, encode all the data of the quiver. And these theories are indeed related in pairs by mirror symmetry, which acts exchanging the 2 partitions sigma and rho. An important observation is that all these T sigma rho theories can be obtained by turning on some nilpotent web for the X and the Coulomb branch moment maps of the TSUN theory. But the problem is that in general, these webs are quite difficult to study. And indeed, usually we rely on an Anali-Witten brain realization for this class of theories, in terms of which the action of mirror symmetry can also be understood quite well. But the problem is that now we would like to draw some analogy between 3 and 4 dimensions. So we would like to define a new class of 4D theories, which are obtained from EUSP2N by also in this case turning on some web for some of the operators of EUSP2N. But the problem is that for EUSP2N, we don't have a brain realization. So what we did in this paper with Chiung and Sarah was to develop a way to systematically study all these deformations, which is based only on field theory techniques. So in this way, we managed to study these deformations of EUSP2N, which led us to define a new class of theories, which schematically are represented in this quiver. And again, all the data of the theory can be encoded in these 2 partitions, sigma and rho. So by analogy, we labeled these theories E sigma rho of USP2N. And we also managed that all these theories are related in pairs by an infrared duality, which acts exchanging a sigma and rho. So we called this new type of duality mirror-like duality. So as I said, this was not a direct uplift of results for 2D free fields. So let me go back to the original topic of my talk. So in our papers, we managed to find many new dualities and global symmetry enhancements in 4 and 3 dimension by uplifting the results for 2D free field correlators. And to conclude, I would like to show you an example which actually is still a work in progress, and which is based in this case on the 3-point function for Todai-2 theory. This 3-point function has an invariance under the action of the Weil symmetry group of E6, but this invariance is not too much surprising if we think that under AGT, the 3-point function of Todai-2 is related to the T3 classes theory, which is also known as the E6 Minane-Mechansky theory, which indeed has an E6 flavor symmetry. But from the point of view of the 3-point function of Todai-2, this invariance was proved by Fatev and Litvinov by using the free field integral representation of this 3-point function. In particular, they managed to prove that this free field integral is invariant under a transformation of the free momenta. Now, applying our strategy, we can look at this free field integral and try to read out of it a 4D equal 1 gauge theory. So this is what the 4D equal 1 gauge theory looks like. And in this case, we have 2 gauge nodes because we are starting from Todai-2. In Todai-2, we have 2 sets of scaling charges, and this translates into 2 gauge nodes in the quiver. And the invariance of the free field integral basically translates into a self-duality of the theory, which can be understood as an invariance of the theory under some action on the global symmetries. So this means that the theory in the infrared has some additional invariance on top of the UV global symmetry. And in general, these additional invariances may lead to an enhancement of the global symmetry in the infrared. Indeed, it seems that this theory enjoys an E6 global symmetry enhancement in the infrared. But as I mentioned, this example is still a work in progress. So to conclude, I would like to just repeat what I showed you in this talk and leave you with some possible open questions. So I showed you a series of limits that relate 4-dimensional supersymmetric gauge theories to 3-dimensional theories and eventually to 2D free field correlators. And then I showed you that we can try to, in a sense, reverse the logic of these limits to find new results, new dualities, and symmetry enhancements in 4 and 3 dimension, starting from known results for 2D free fields. So the immediate question is if we can extract even more results from 2D free field correlators. Indeed, there is a lot of some literature on these free field correlators. I also showed you a new class of 4D n equal 1 infrared dualities that can be understood as an ancestor of the 3-dimensional mirror symmetry. And it would be very interesting to understand if we can find a 4D origin also for other mirror dualities, like for the star-shaped quivers. I also mentioned that we have an understanding of mirror symmetry in terms of branes in 3 dimensions, while we lack a brane setup for our 4-dimensional theories. So it would be interesting to find a brane realization of our 4D theories or some other geometric realization. And finally, it would be interesting to study better the structure of the moduli spaces of our theories. We know that 3D n equal to 4 theories have a moduli space with an hyperscalar structure. Of course, we don't have any reason to expect such a structure in 4 dimensions because we have less supersymmetry, but still we can try to understand if the moduli spaces of our theories enjoy some interesting structure. And finally, I tried to stress the fact that our approach, which is bottom-up, goes in the opposite direction of the more standard approach of compactification from 6D. But I showed you a point where it seems that the 2 approaches make contact, and I think it would be very interesting to try to understand if these 2 approaches can be somehow unified or related in any way. So with this, I conclude, and thank you for the attention.
Thank you. So we have time for 1 or 2 questions. Yes, Craig, please go ahead.
So actually that was the clapping hands
Oh,
rather
sorry.
than the, but I will ask a question
I'm
anyway.
sorry.
Thank you.
So for the connection to the 60, so the ones that you can match at the moment to 60 are just compactifications of the E string on fluxed tori.
Yeah.
Is there so is there a reason why you can match those ones, or is that kind of a this is the obvious thing to start with?
I mean, I don't have an understanding of why this theory, I introduced this theory in this way from this bottom-up perspective. I don't have an understanding of why it appears also from this other top-down perspective. So this is what I think would be interesting to understand better. But yeah, it seems that this theory appears only in this context of the compactification of the string for some very specific choice of fluxes. Actually, not directly this theory, but it's like a slightly more complicated quiver gauge theory that uses this theory as a building block. Because once you have these two USP2N symmetries in the infrared, you can use the SCFT that lives in the infrared as a building block to construct more complicated models.
Oh, I see. So it's quite intricate, the relation between 60 and the models you're building.
Yeah, for the tube model, so the compactification of the tube is not too difficult. You just have to imagine that you have this USP2N theory, and then you should add just some chiral singlets. So it's not too complicated. But when you start to construct tori, then the theory becomes slightly more complicated than just this USP2N. But yes.
Ah, interesting. Okay, thank you.
Okay, so I suggest that maybe we thank the three speakers for the first part. Thank them again. And so I invite actually all the speakers to show up and everybody to ask questions to all of them. So you can raise your hand, and if I don't mistake it for clapping, I will try to, or you just unmute yourself and talk. Okay, Stefano is not clapping and asking question. Please go ahead.
Thank you. I had a question for Or. So if I take your one of your exactly marginal operators and I multiply it by another chiral operators, that operator will also be nilpotent, but it will have a nilpotency index which is less than or equal to the index of the nilpotency index of the exactly marginal operator itself. So I was wondering if you looked at this richer structure, if you can say anything about that.
No, we didn't look at it.
Okay, thanks.
So actually, I also have a curiosity for Or. So when you say that, I mean, do you have any hint of whether it is possible to extract this nilpotency index from some partition function as a limit, or it's just?
So the answer is no. I tried to play with the superconformal index. Because like the least amount of cancellations happen in generic points, and this nilpotency index is also a generic point. So maybe, but it seems like there are many different kinds of multiplates other than the chiral multiplates, and with many cancellations. So it didn't seem, I didn't find yet a way to get it or to relate it to other partition function. I mean, the most related object would be the Hilbert series, but then, I mean, you should find a way to calculate it for these theories or claim invariance and whatever. But I think it's actually more interesting that it is not extractable because, okay, I mean, there are two, even if it is abstractable, there are two options. Either it is in some more universal way, and then, okay, two theories with the same function will necessarily have the same index, or the abstraction prescription itself may depend on, then it is less trivial. But I think most interesting result is that it is not extractable, and then it's a new thing. Yeah.
Thank you.
I sorry, also have a question, not to bother you, but if you go back to the example of n equal to 2 theories, and instead of taking an n equal to preserving marginal operator, you start from an Higgs branch operator of dimension 3/2 of R charge 3/2.
Which theory are we talking about?
Just a generic n equal to SCFT,
Yeah.
such that it has an Higgs branch operator of dimension of R charge 3/2. So of dimension 3. So I think these guys are going to contain n equal 1, exactly marginal operators upon from n equal to 2 to n equal 1.
So what is the claim again?
So the claim is that if you want to get in n equal to 2 superconformal field theory, and you want to know which n equal 2 supermultiplet contain n equal 1 exactly marginal operators. Okay.
Yeah.
And the claim is one is the one you showed. So
yeah.
an exact, but the other one I think are X branch generators of charge 3/2. I think that is the claim. I mean, is that I'm pretty sure is that a composition of of representation from n equal to 2 to n equal 1. And I fail to see how this object can be nilpotent. That's my small confusion.
So you are claiming this these operators will also yield something which is exactly marginal in n equals to 1.
Yes. And I think Slum also considered. I mean, this example when they recently found strongly coupled n equal 2 theory in the conformal manifold of some n equal 1 theory. These are you move from this n equal 2 theory exactly with this sort of marginal deformation, X branch type. My question is if you can see in this example how the nilpotency work, because I cannot see.
So you're referring to Lagrangian theory?
In their work, they do Lagrangian theories. I'm just trying to see abstractly how, or whatever example.
Yeah, so I need to think a bit about this way of getting n equals to 1 exactly marginal operator, which is not obtained from as a descendant of a Coulomb bridge. I'm not sure. I'm not sure. I need to think about it a bit. So you are claiming to have a theory with Higgs branch operator.
Yes, which is n equal 1 chiral.
And then you're saying that which is chiral with respect to the n equals to 1 subalgebra.
Exactly. Yes.
Yes.
Well, I think that in order to build an exactly marginal deformation, you need both an operator charged under U1R and another one charged under SU2R, both of dimension 3. If you just have an X branch generator, this will be marginally relevant.
This is what I think.
So probably the statement is that the nilpotency of a specific linear combination of the two will be nilpotent.
Okay, I mean, you're saying that there is some sort of the analog of the Cornish anomaly that relates one to the other, and
yeah, exactly. But there will be a linear combination of the two which doesn't get any anomalous dimension, and that will be exactly marginal. But if you have only one of them,
yeah,
probably not. That will be irrelevant.
But the mechanism by which it becomes nilpotent is exactly because a combination is zero in cohomology. I mean, is co-exact, and I mean, one combination is anomalous, so it's a zero, right? The combination that gets anomalous dimension, you can think it as a zero combination, so you solve for one in terms of the other, and so the X branch generator becomes nilpotent, right?